A block hangs on a spring attached to the ceiling and is pulled down 8 inches below its equilibrium position. After release, the block makes one complete up and down cycle in 1.2 seconds and follows simple harmonic motion. First thing we're asked to do is write a function to model the displacement d in inches as a function of the time t in seconds after release. Assume that a displacement above equilibrium position is positive. So we want to remember the kind of formulas and things we have for simple harmonic motion, but we don't want to neglect that this is really just sketching a graph and finding an equation for that graph. Well, what we knew was that our model is either going to be a sine model or a cosine model depending on its starting point. So let's begin to sketch this out. We have our set of axes here, and we are told that this is pulled down 8 inches. So it's pulled down to -8. And since this is following simple harmonic motion, it's going to go back up to 8 and then come back down. And that's exactly what's going to happen. It's going to go to 8, it's going to hit equilibrium, up to +8, it wasn't -8, sorry about that, back to equilibrium, and then back down. So following this type of model. This helps us to determine, are we looking at a sine situation or a cosine situation? Well, when we're starting at 0, if at time 0, if at the beginning of the situation you're at equilibrium, that's going to be a sine function. Here at the beginning of our situation, we are 8 inches below equilibrium. This is a cosine situation, so that tells us this is the model that we're going to use. D is equal to A times the cosine of omega t. Well, that looks like cotangent. Still looks a little like cotangent, but hopefully you can tell what it is. All right, so this all happens in 1.2 seconds, so let's keep that in mind as well. We have an amplitude of 8, but it is flipped, so we will remember to put a negative sign in there. Then we want to think about, okay, how long does this take to happen? Because that is going to influence what omega is. The period, P, is given by 2 pi divided by omega, which means omega is going to be equal to 2 pi divided by P. Well, the period, how long it takes to complete a cycle, is 1.2 seconds. So omega is 2 pi over 1.2. You could use that as your omega, but we're going to simplify it to 5 pi over 3. Just on your calculator, do 2 divided by 1.2, and you'll get 5/3. All right, so now we know omega, we know the amplitude, that we have that negative. So for part A, our model, the displacement at any given time is going to be equal to -8 times the cosine of 5 pi over 3 t. All right, so there's the formula for our displacement. Part B says, find the displacement of the block and the direction of movement at t equals 0.3 seconds. So we will plug in 0.3 for t, giving us -8 times the cosine of 5 pi over 3 times 0.3. Making sure that your calculator is in radians, we get 0. So that means this block is at its equilibrium point. And then the question becomes, is it on the way up or is it on the way down from there? Because it could be at the equilibrium point going on the way up or the equilibrium point going on the way down. A couple of different ways you can think about this. If 1.2 is the period, and you know we've got this divided up into our 4 sections here. Let me highlight that a little bit better so you can actually see that it's 4 sections. Then this is going to be 0.3, this is going to be 0.6, this is going to be 0.9 seconds, and that would be 1.2 seconds. So at 0.3, we can actually see that we're at the equilibrium point and we're on the way up. If that's not as readily observable to you, just plug in a little bit larger t-value, like maybe 0.4. Don't get too big. You could even do 0.31. You want to stick really close to that t-value. What you would get would be a positive number that would also tell you you're on the way up. So the block is at the equilibrium point and on the way up. The next thing that we are asked to do is find the displacement of the block and the direction of movement at t equals 4.7 seconds. So we will plug in 4.7 to our model, -8 times the cosine of 5 pi over 3 times 4.7, and we get -7.1. So that tells us the block is 7.1 inches below equilibrium. This is a little bit more challenging to tell whether it's on the way up or on the way down based on the time because it's so far past there. It could be done, but I would just suggest maybe plugging in t equals 4.8. When you do, you will get that you are moving downward. So the block is 7.1 inches below equilibrium and moving downward. And then the last question that we are asked is to find the frequency. The frequency is the reciprocal of the period. Okay? So it takes you get one cycle in 1.2 seconds. So what we want to figure out is how many seconds per cycle. Well, that's the reciprocal. So we would do 1 divided by 1.2, and we would get 0.83, or if you wanted to give that exactly, that is 5/6.